All right, I'm Siegfried Janson. I'm with the Aerospace Corporation in El Segundo, California. And I'll be talking about two NASA Innovative Advanced Concepts efforts. One was funded, that's the first one, Spacecraft Phase 2. And because of the nature of this conference, I thought I'd spend a few minutes talking about something that I submitted a number of years ago called Smart Propellant. I'll get back to that after this one. So I'll start out with Spacecraft. And the idea for Spacecraft is to perform active orbital debris removal. You've heard a number of people say orbital debris is an issue. Some people want to corral it in space. I tend to agree with that. It's more useful in space than it is burned up in the atmosphere. But the simple thing about it is it's easier to drag something straight down and burn it up in the Earth's atmosphere than it is to put it into other orbits, especially if the orbits have higher inclination. But the idea for the Spacecraft was to see if I could produce a mass-producible spacecraft that made economic sense. And what I came up with is a very thin film spacecraft. It's a membrane spacecraft, hence the name Spacecraft. And the idea is you mass produce these. They're ultra low weight, and they're ultra low weight by making them very thin. I'll get to that later. And the idea is you put a bunch of them up on, say, the International Space Station, and you give them individual targets in low Earth orbit. It could be anywhere in low Earth orbit, where low Earth orbit's defined as from about 200 kilometers out to 2,000 kilometer altitude, any inclination. They start out from there. You program them one by one, which piece of orbital debris you want to go after. They thrust, they rendezvous with the target, they wrap around the target. That's why you see the curved shape here. And then they start thrusting. And again, to get to the target is the tough part, but the Spacecraft doesn't weigh much. These things weigh nominally about 80 grams, but they can remove kilogram-class objects from low Earth orbit. Once they wrap around, they thrust, and then they just spiral down very quickly and burn up in the Earth's atmosphere. If propellant's still available, you can go after another object in space. Now, the idea was to make it economically feasible. Normally, you might think, oh, I want to use CubeSats for this purpose. The problem is a CubeSat, it's going to cost you probably $250,000 for a 3U CubeSat with propulsion capability and navigation capability. And then you're going to have to add another $150,000 to $200,000 to get it up into orbit, because that's what launch costs are these days. But what if I can shrink that mass down, again, down to 80 grams or so? It allows me to bring down 5,000 objects using maybe a few $100 million of non-recurring, or recurring funding. The problem is there's a lot of non-recurring funding you got to spend up front, but if you want to do this using the normal technique, it costs about $2 billion to bring down 5,000 kilogram class space objects. So the Spacecraft offers a way of doing it much cheaper, but you're going to have to spend some money up front to do the R&D required. Now for this conference, it turns out the Spacecraft can do other things than bring down orbital debris, and I'll get to that later. But again, the idea is we go ultra thin. The Spacecraft is composed of 10 micron thick Kapton sheets with all the electronics and systems basically printed on them. And that gives you a number of headaches, but we're working on solving those. Thin film solar cells, 82 gram mass, electric propulsion, and you want to be able to build these in 1,000 units and larger lots. Otherwise, it just gets too expensive. So the basic design here are cross sections. On the left is the Spacecraft. These yellowish sheets are the main structural sheets. Again, it's 10 micron thick Kapton. They're electronic sheets bonded to that. And between these main structural sheets, there are spacers and there's propellant in between. The propellant in this case is an ionic liquid. Think of table salt that's liquid at room temperature. That's the propellant for electrospray thrusters. This is the latest generation of electric or ion engine that uses liquid propellants. And these ionic liquids have an interesting feature that they have almost no vapor pressure. What happens if you try to boil salt? It turns into a liquid, but then it doesn't really boil. You don't get chlorine gas off salt. It takes really high temperatures to do that. Ionic liquids are the same. You can store them in an open bottle in space. So basically it's held between the Kapton sheets using capillary action, and then we can use electroosmosis and other techniques to move the propellant around to the thrusters that need them. So these are micro-pattern thrusters, and that's the tricky part. But again, this is a technology that's being developed by NASA and other space agencies today. Some of these parts have flown. We've flown some on CubeSats. And they'll be ready in about 5 years or so for this type of an application. I compare that to a flat panel display screen. This is another device of modern technology. A 4K television, if you decided to cut through it, you have two pieces of glass, you got some polarizers, there's a liquid crystal between the glass, and there are electrodes and transistors, and these transistors decide whether or not to turn on a voltage between the two pieces of glass. And if they do, the liquid crystal twists, and that changes the polarization of light going through it. So if they're off, you get no light. If they're on, you get light. And then there are a bunch of color filters that tell you whether it's blue, green, or red. So it's a very similar design. The only difference is I'm not using thick glass panels. I'm using flexible Kapton sheets. The reason I went to the smaller electronic sheets is that these things, flat panel displays are made in China now, and a foundry for one of these, for making televisions or computer displays, typically costs about $5 to $6 billion now. And the reason they cost so much is you go in with sheets of glass that are about 3 meters square. You process that, and then you cut out your individual displays afterwards. If you start with smaller elements, you can make that foundry a lot cheaper. So what did we learn in phase 2? It started out as a phase 1 back in 2016. You saw the basic cross-section. We discovered a number of issues, one of which was the radiation problem. There's essentially no radiation shielding on these Brane craft. So we have to print electronics that can survive very high levels of radiation, Cold War space type radiation levels. We need 5 megarads. And that's what we're doing. We're now fabricating zinc oxide logic gates, and we want to supplement those with carbon nanotube gates so we can do complementary metal oxide semiconductors. We've tested some muscles. We've designed a micrometeoroid proof interconnection system. Turns out, space environment might seem kind of benign, but if you look at pieces of windshield, from the shuttle and solar cells that have come back, you notice a lot of little pitting on board. Bottom line is a square meter spacecraft exposed to 1 month in the low Earth orbit environment will have about 40 holes through it if it's composed of 10 micron thick Kapton. So we have to design the Brane craft to handle about 40 punctures. So that means you need a command and control system that can handle faults. We have to be able to lock out individual processors, thrusters, things like that. So we've designed a system that can do that. Turns out the solar rays actually aren't that bad. There are thousands of solar cells, but as long as you put a diode in between each one, they naturally are immune to breakage, open circuits and short circuits in the individual solar rays. They're thin film solar rays, and you might say, oh, that's kind of a hard thing to do, but turns out a number of years ago, I think it was 4 or 5 years ago, 7% of the world's solar cell production was thin film solar rays. So we're just kind of adapting that technology for space. And it turns out, the cadmium telluride and other technologies are actually quite radiation hard. So that looks very promising. And finally, the Brane craft can explore most of the solar system. I'll zip through these as fast as I can. Again, we're working on radiation-hard thin film transistor technology, and what I'd like to point out is, here's a simple transistor layout. You got a gate, you got a source, a drain, you got some insulators, a gate oxide. Electronics are made using deposited materials. They're 3D printed surfaces. The only difference between that and what we call additive manufacturing is there's a lot of subtractive manufacturing going on in your integrated circuits. You put down layers, you put down photoresist, you pattern it, and then you get rid of most of the stuff you don't want, and then you put another layer down. So making 3D structures small is something that's been going on for 30, 40 years. We want to make radiation-hard structures. We've redesigned them a little bit to make them even more radiation-hard. I don't think I need to go too much into this, but we're fabricating them on polyimide film. This is basically Kapton. So we put polyimide film on silicon, your normal material for making microelectronics. You deposit your materials on that, and then you peel off the polyimide film. Here's just an example of one of the masks we've designed. Lots of transistor shapes, some logic gates, and basic structures. First fabrication results, we had some issues. The number of transistors were shorted. Turns out the photoresist was too old. But now we're on our third run, and we've got working devices on board, and we've been able to show some current voltage characteristics. Those are off too. We believe that's due to charge buildup in how we're depositing the layers, so we're working on fixing that. But we're on the road to making rad-hard electronics that you can deposit on film. And the interesting thing here was that the field effect mobility was about 30 centimeters squared per volt, which is comparable to what other people needed. It also tells us that I can build 1 micron scale transistors on this meter square sheet, and they'll be fast enough. You'll have microprocessors that can run at 10 million instructions per second and faster, which is what we need. So basically, we can print the command and control electronics we need on these thin Kapton sheets. We've done some micrometeoroid proof design. Again, bypass diodes. AC coupling of signals between the processors turned out to be a good way to go. Because normally if you have a processor with a locked gate and that I/O gate is connected to another I/O gate and another processor, it drags down that particular bus. You want all your buses to be able to handle shorts and open circuits at either end. We're also designed a mesh network architecture so that they can talk to each other and turn each other off when necessary. And one thing I didn't mention was the distributed dynamic propellant storage. These ionic liquid propellants are great because they have no vapor pressure, they're liquid. The significant disadvantage is they're electrically conducting. A lot of ion engines use xenon, argon. It's a non-conducting gas. When you run an ion engine, the outer grid's at spacecraft ground, but somewhere you have elements that are at kilovolts with respect to the outside of the spacecraft. That means your propellant's at kilovolts. So we have to deal with that in the Brane craft too. And what makes it worse for these electrospray thrusters is they actually swing positive and negative about once a second. So they go up and down a kilovolt. Yeah, it's a challenge. We need muscle actuators. You actually need to be able to curve the Brane craft, not only for wrapping around your target, but for basic stability. If I hold a sheet of paper in one atmosphere, right, it kind of curls down. But if I put some curvature in it, I can support gravity. So you need some curvature, and that's the purpose of some of these actuators. Design some sun sensors. You need all your basic spacecraft systems and subsystems to be redesigned to be printable on surfaces. Now we've done something not quite the same, but for CubeSats, we ended up redesigning just about every spacecraft system and subsystem because typical things like sun sensors used to be the size of my fist for normal-sized spacecraft. We got them down to pinky size, and now we're getting them even smaller. The next step is to make them essentially two-dimensional. Where can Braincraft go? Okay. On the right, I don't know if you can see the numbers, but that's a subway solar system map. And the Braincraft start out down here at the International Space Station. That's the home port. These numbers are the delta V's in meters per second required to go to these various destinations. So for the basic orbital debris removal, these are the blue ones. If I want to go up to a 1,200 kilometer altitude orbit that's in sun-synchronous orbit, that requires 5,820 meters per second for the basic Braincraft. And suddenly realize, those are kind of high numbers compared to other things that you may want to go to, like the moon. If I want to go to GEO, put up a geosynchronous satellite, it's about 4,200 meters per second. So it's actually harder to get to low Earth orbits that are inclined than it is to go out to geosynchronous Earth orbit. It's easier to crash into the moon than it is to put a satellite at geosynchronous Earth orbit. So this kind of gives you a feel for it. And the bottom line is that a Braincraft by itself has a delta V of about 16 kilometers per second, and we can we can change that depending on how much propellant we put in there. But with 16 kilometers per second, you can go all the way out to one of Mars's moons, Phobos or Deimos, I forget which way to say it. But you can go all the way out there, collect a little bit of dust, and come all the way back. So that's what 16 kilometers per second does for you. And because it's so light, these things accelerate not like typical electric thrusters. They accelerate not like typically electrically propelled spacecraft. They accelerate more like chemically propelled spacecraft. The acceleration in full sunlight is 0.1 meter per second squared. If I want to go, oh good, it shows up here but not on this screen. Starting out from the International Space Station and just running the thrusters, and there's a lot of shadowing going on, but this is the trajectory. This is altitude in kilometers versus time in seconds. 8,600 and 400 seconds is 1 day. So within 1 day, I'm already up to about 18,000 kilometers, and within 2 days, I'm on my way out of the Earth's gravitational field. Total thrusting time is like 36 hours for these thrusters. Earth escape occurred at 38.7 hours. Let's see, it spent about 21 hours in the main radiation belt. So what I was interested in is how much radiation does it pick up on the way out for interplanetary applications? And it turns out that number is only about 0.7 megarads over that length of time. So it's much less than what it's designed for to do the orbital debris removal mission. So it looks like Braincraft can be used for interplanetary missions. You can go out and visit thousands of asteroids. In many cases, you can come back with a piece of dust, but at least you can go out there, image them, maneuver around them, get some idea of what the gravity field looks like, and hopefully determine whether it's a rubble pile or a solid rock, which is very important if you want to mine the thing. So the significant impacts for this is that in recent years, we've fabricated rad-hard, well, we still have to test rad-hard, but pretty sure they're rad-hard, or N-type thin-film transistors, the zinc oxide ones. We've got a micrometeoroid-proof design. We've tested a muscle actuator. We're actually going to a different one because this one's thermally based, and because of eclipses, you just can't do a thermally based system. And there are electroactive muscle designs that use the propellant itself as the mechanism, because turns out if you choose an ionic liquid where the cations are a different size from the anions, so the negative guys, say, are bigger than the positive ones, if you run a capacitor, if you try to run it like a capacitor, the big ones go one side, the smaller ones go to the other side. The big side will try to expand, so that gives you a curvature actuator that you can build right into the spacecraft itself. I think I've shown you that the Braincraft can be used on interplanetary missions. So the plans for next year are to fabricate and test, actually do the radiation testing on the thin film transistors, fabricate carbon nanotube transistors. That's where we wanted to go first, but we decided to start with the zinc oxide transistors. And then we have to design and build a number of sensors based on those. You need photodetectors. Silicon photodetectors will die in these radiation levels. We need carbon nanotube and zinc oxide based ones. And we have to fabricate and test new muscle actuators. The real challenge, though, is that in any spacecraft, there's usually a crystal somewhere, and that's a timing reference. The quartz crystal oscillates. We still have to figure out how to do that in a thin film form. So that's one long-term issue that we have to solve. But it looks like these can work for orbital debris removal, which was the original application. And beyond NIAC, what we'd like to do is just step through the technology. We're at like technology readiness level 2 to 3. How do you go to 4? Well, you start tackling some of the harder things, test them on the ground. And that's like building complete radiation hard, thin film microprocessors. So we'd like to start out with, say, a 4-bit processor and then work our way up to a 32-bit version that we can print on Kapton. But again, these transistors, it's not like the current generation of transistors where your minimum feature size is like 20 nanometers or less. These are micron scale transistors. They're fairly easy to fabricate using cheap photolithography. And that's the whole point here. We want to be able to mass produce them. So now I think I have some time left. That's where we are now in the Braincraft. This is very promising technology funded as a phase 2 NIAC. Number of presentations. I'd like to thank NIAC for funding us. The bottom line here is this vehicle that we're developing for orbital debris removal looks like it can be used to maneuver through a lot of the solar system, at least out to Jupiter, where the solar power levels start dropping. It can't land on things with a gravity higher than 0.1 meter per second squared, but you can certainly orbit them, and there are many asteroids that you can go explore and make contact with using Spacecraft. Now I'd like to talk about something called smart propellant. This was a proposal I submitted to NIAC a number of years ago. It wasn't submitted because it was deemed at the time to be a little too far out, but this is in response kind of to the lecture that I'm sure Dr. Lubin gave yesterday on laser propulsion, because if you listen to that carefully, it sounds like he's saying, rockets, who needs rockets? Lasers can do everything. And there's a lot of truth to that. But what you have to do is rethink what you do with propulsion. So in the standard rocket, propellant is lost after use, right? It's like me standing on a skateboard or a hovercraft with a basket of balls. I throw my balls to accelerate. When I'm out of balls, that's it. I can't do anything else. But what if I could recycle those balls? What if I could recycle my reaction mass? I could throw it at a wall over there. If I threw it just right, I could catch it, and then I'd get my reaction mass back. That's the idea of smart propellant. Can I use not molecules as propellant, but small objects that have their own navigation systems that allow them to come back and allow me to recapture them? And what that does for you is it breaks the problem of the rocket equation, right? Because normally you want to go up in propellant mass to get high velocity increments, but the only way to do that, you want low mass fractions, the only way to do that is with high specific impulses. That means a lot of power going into it. And the flip side of that is that the power costs you dearly. And here's a plot of the propellant energy density in megajoules per kilogram. This is the blue line. The red line is the power per Newton. So if I use lasers, the power per Newton's up here somewhere. It's like 150 megawatts per Newton if I reflect light. But if I can use particles, now I'm down around into the tens of kilowatt level, even with specific impulses that are 10,000 or so. So that's like 100,000 kilometers per second. It's not as easy to reflect particles as it is to reflect light, but it gives me an option of using much less power to generate a unit of thrust far from the home planet or wherever my generator is. But for smart propellant, everything's in the spacecraft. So what you do is the rocket ejects propellant, and then through some orbital mechanics, you can get the propellant back, and that's if you're smart about how you eject the propellant. I'll show you some applications. So basically you're using a mass driver, an electromagnetic accelerator, throw mass out, comes back, and then you catch it and you regain that energy and mass. His orbit rephasing is a simple application. You have a satellite orbiting the Earth, you kick something out, it goes into a different orbit, you catch it at a different time. Your spacecraft essentially moves along the arc. So you've moved it without expending any main propellant. That's the easy one. And the velocities are quite low. I think a baseball pitcher could do this. And here's just some more details about that. The propellant goes one way, spacecraft goes the other. The trick is to eject it at just the right velocity so that you can catch it when you're at perigee, at the same time. Now, we can go through there's different, you can look at it in a rotating reference frame. But again, the bottom line is ejection velocities become quantized. So if you eject it at just the right velocity, your spacecraft does n orbits. The propellant comes back after n-1 or n+1, depending on whether you threw it higher or lower energy, and you recapture it. You can also use it to just kick something out for a while into a highly elliptical orbit and catch it afterwards. That's one way of using it as a high-altitude probe. But landing and takeoff from the moon I thought would be more interesting for this group. If you have a bunch of propellant, say you have something orbiting the moon, you got a spacecraft orbiting the moon, and I want to land. One way of doing it is shooting out a bunch of mass into an elliptical orbit. Enough mass that the lander essentially goes to zero net velocity with respect to the moon. So it drops down to the moon. Now, you don't want lots of distance here. Ideally, you'd like to do this at 1 to 10 kilometers above the moon. But if you did that, this propellant mass would go into an elliptical orbit. And there are limits on how much propellant you can throw out there because you can't throw it too fast, it'll escape. So it has to be you can only eject it at a speed less than 41% of the circular orbit speed that the lander's doing. But in principle, the lander will drop, this mass stream will continue around, and when you're done with your lunar mission, you pop up and you recapture it, and then you end up back in your initial state. So that's how I go from, I'm up here, I've landed, and I've gone back up. Now I still need to have propulsion for the actual landing maneuver and taking off again, but that's a lot less than trying to land from a complete lunar orbit. So that's the idea. It's pretty simple, but again, in practice, the devil's going to be in the details. It's up to us to find the angels in those details and get these things to work. Here's some just basic calculations, the velocity ratios. Again, you can't eject at much higher than 40% of your orbital velocity because then you'll lose your propellant. It's an escape orbit. But if you compare this to using propulsion, using 311-second ISP thrusters, this is a good space-storable hypergolic propulsion ISP. If I want to land on these different bodies, here the surface orbit, escape velocity, the propulsion mass fraction for one landing for something like Phobos is pretty light because it's a small body. But as I go up to something like the moon, it's about 67%. And it turns out to do the smart propellant, you actually need about 71% of your initial mass as propellant. But you keep getting it back again. So the bottom line here is I can do it multiple times. I could do one landing, 2 landings, 6 landings. And it's when you do lots of landings that you realize that the smart propellant applications could be a real good way of going. I'd just like to show this one final thing. There are lots of ways of using orbital mechanics to get your propellant back. This is another way. It's called the Apoapsis reflection maneuver. If you've got a spacecraft orbiting a planet or a star, you shoot mass in one direction so it goes into a very highly elliptical orbit. The thing to realize is that linear momentum is not conserved in an orbit, angular momentum is. So when your mass particles get far away, they're traveling much slower than they were up here. So in principle, you can get, if you kick it into a highly elliptical orbit, maybe a few hundred meters per second will allow you to reverse direction and cause them to come back where they're recollected by the host spacecraft. So there are a lot of these mechanical tricks that may work in the near and midterm future. They look promising, but they're all going to need lots of space traffic management in the future. And I think I'll just stop it at that point.